Hello and welcome back to Probability Theory. And you might already know, first I want to thank all the nice people who support this channel on Steady via PayPal or by other means. Now, in today's part 14, we will talk about the expectation of a random variable. And in this regard, we will also talk about the change of variables formula. Now, as always, we need a probability space consisting of a sample space omega, a sigma algebra A, and a probability measure P. And then we will consider a random variable x. In particular, it should be one that maps omega to the real number line. And there, often it's possible to define a so-called expected value for the random variable. And this one is often denoted with bold E of x. Now, the first important property here is it's an element in this set, so a real number. In fact, I call this number the expectation of the random variable x. However, please note there are a lot of similar names for this number. For example, as I told you before, you also often see the name expected value. However, you should see all these names explain that e of x is the number the function x is fluctuating around. So in some sense, it should be the mean of the random variable. And I guess best to see this is in the continuous case. Because there we know the random variable x has a probability density function, a PDF. More precisely, you would say it's the PDF of px. And here please recall, a probability density function is a non-negative function where the integral is exactly 1. For example, that could be a symmetric function that looks like this. And then please note, this integral area here is exactly 1. However, more important for us right now is that you would say that the expectation lies exactly in the middle here. So the value on the x-axis here is e of x. Hence you see, in such a case it's very easy to find the value the random variable x is fluctuating around. However, now of course we will define this in general. So the definition should work for a lot of random variables x. Therefore, the assumptions are the same as before. We have a general probability space and a given random variable x. And now e of x is simply defined as the abstract integral of x. So integral over omega of x dp. Now, maybe at this point you don't have any idea what this means, which is not a problem at all. However, in the case you know measure theory, you immediately see that this is a well-defined Lebesgue integral, if it exists. Therefore, if you are interested how one can define such an abstract integral for a given measure p, then you can watch my playlist about measure theory. However, you definitely don't need all of measure theory if you just consider continuous and discrete cases. In these cases, you don't need to be so abstract. Hence, I would say for this course it's sufficient that you know that such an abstract formula exists. Moreover, also helpful is if you know that an abstract change of variables formula exists. This is a substitution rule that can explain a lot of formulas immediately. And maybe the best way to explain it is using a picture. So this here should be our space omega, and inside we find a measurable set A. And surely this A should be an element of the sigma algebra A. And now our random variable x maps from omega into R. So the values of x lie on the real number line. However, now we could have an ordinary function from R to R. And this function here should get the name g. For example, this could be the quadratic function that sends the variable to the variable squared. In fact, exactly this example we will use a lot. Because there you should see we can formulate a new random variable g after x. And indeed, often you see this written as g of x. In fact, in our example from before, this would be x to the power 2. Now, the important thing to note here is that this is a new random variable, where also the expectation can be interesting. And now it turns out this new expectation is related to the old one. And exactly there, the change of variables formula comes in. Okay, the starting point is this abstract integral, now with the function g of x. Again, as before, if you don't know what this means, it's no problem at all, you can see it as a symbol. And then what follows will be a symbolic calculation. But before we do that, first I want to change the domain here to the set A. Then the formula is just more general. Now, in the first step I can tell you there's also another way to write down this integral. It's exactly the same thing, but it uses a variable name, here lowercase omega. And there you see, change of variables now means that we introduce a new variable. In our case here, this means x of omega should be named to a new variable. And often we just call it lowercase x. Therefore, you could say x inverse of lowercase x is our lowercase omega. Okay, and then you can do the same things you might already know from the ordinary substitution rule for integrals. First, the domain of integration is the image of a under x. And then we just have the function g of lowercase x. However, now the measure is different, it's p composed with x inverse. And there you know, we read this as a pre-image, and therefore this should be the distribution of the random variable x. In other words, it's px. In fact, this whole thing here is very important, it's the first thing you should remember here. More precisely, this means this abstract integral here can be written as a more concrete one, as an integral over the real numbers. Still, we could have another measure here, but this one is now defined on the real number line. And indeed, the whole thing gets much simpler when we just consider discrete and continuous cases. So maybe let's start with the continuous case where px has a probability density function. This means that now we should have an ordinary integral, which means we can write dx. And the important thing we have to include here is the probability density function denoted with lowercase f index x. So this is the PDF that describes the probability measure px. In other words, if we are in the continuous case, this abstract integral here can be read as this normal integral. And on the other hand, as you might already know, in the discrete case, this should be given by a sum. Or more precisely, it can be a series. The important ingredient here is of course that in the discrete case, we have a probability mass function for px. And we could denote this with lowercase p and index lowercase x. There you just need to know that this is the probability measure of the singleton x. Indeed, in the discrete case we know we have at most countable many of these singletons where the measure is non-zero. Therefore, this gives us a so-called probability mass function of our probability measure. Okay, and now you should see this abstract integral here is not complicated at all in these two cases there. However, even in the case that you only need to calculate with these two cases here, it's also helpful to use this abstract integral as a short notation. Okay, with this in mind, let's go back to the expectation. There we now get two formulas for the two cases. Please recall, we defined e of x as the abstract integral for g as the identity function. This means the two cases on the right hand side are not complicated at all. So we don't need any g at all, we just have the variable x. And more importantly, instead of a, we have omega here. Therefore, you often see the range of x here and there. However, often the probability density function as well as the probability mass function are defined in such a way that there are zero outside of this range. Hence, you would simply see the real number line r here and there. Okay, so you can remember the expectation of a random variable can be calculated with an integral or with a sum. And maybe to close this video now, let's look at a simple example. Here, let's take again an ordinary die and let's throw it one time. Hence, we have our random variable x from omega, which is 1 to 6, into r. Now, maybe this is not the most exciting example, because the random variable is just the identity here. Nevertheless, I think it's a good starting point to get an idea how to calculate the expectation. Now, in our example here, we are in the discrete case, so we get out a sum. And indeed, it's a finite sum because the range of x is simply the set 1 to 6. Therefore, we have 1 times 1 over 6, plus 2 times 1 over 6, and so on until we reach 6 times 1 over 6. So you see, because the probability mass function is very simple here, the calculation is not hard at all. And then we can just calculate the sum and we get out 3.5. Hence, this is the value we expect of the random variable. Therefore, one important thing you can immediately remember is that the expectation does not have to lie in the range of x. Or in other words, it does not have to be a possible outcome of the random variable. It's just a calculated mean of all the outcomes. Okay, with this I would say let's discuss more properties and more details about the expectation in the next video. Therefore, I really hope that I see you there. Have a nice day and bye!